The universe begins in a silence so fragile it feels impossible, a silence that should have shattered long before anything could take shape. And yet, from that silence, a perfect balance emerged, a harmony so precise it defies every expectation of chaos. Gravity fell into step with electromagnetism. The nuclear forces settled into strength that neither crushed matter nor let it drift apart. Even the mass of the electron landed on a value so exact that the slightest deviation would have erased every star before it even began to glow. It is as if reality found a narrow ledge between nothingness and everything and decided to stand there. But why? Why should a universe capable of collapsing or exploding into meaninglessness instead choose a path where atoms assemble, stars ignite, and consciousness eventually opens its eyes to ask the simplest, strangest question of all? How is this possible? Perhaps the deeper mystery is not that the cosmos exists, but that it exists like this, tuned with an elegance that feels almost intentional. And so we are left with a quiet, unsettling thought. If the universe were even slightly different, would anything exist at all? In the beginning, the universe stood on a razor's edge so thin it almost slipped into oblivion. It was a moment so brief that we measure it in fractions far smaller than anything the human mind was built to imagine. Yet everything that would ever exist depended on what happened there. In that first instant after the Big Bang, the newborn cosmos was nothing like the peaceful night sky we now admire. It was violent, seething, incandescent, a storm of particles flashing into existence only to collide and vanish again. Every quark had its mirror opposite. Every electron was shadowed by a positron. For every breath of matter, there was an answering exhale of antimatter. And the universe, still trembling from its birth, let them meet in catastrophic reunion. They didn't argue. They didn't resist. They simply touched and disappeared in floods of pure energy. This was the universe's first act. Creation followed immediately by erasure, a dance where almost nothing survived. But something unexpected happened in that storm, something subtle, something almost too small to matter. Nearly every pair of particle and antiparticle destroyed itself, but not every pair. Out of a billion collisions, one tiny fragment of matter failed to find its partner. 1 in a billion. A difference so slight it feels indistinguishable from zero. And yet that almost zero is the only reason we exist. Without that microscopic imbalance, that sliver of asymmetry we call baryon asymmetry, the universe would have collapsed into perfect nothingness, a sea of light without form, without atoms, without story. But the imbalance remained, a cosmic miscalculation, a quiet defiance of symmetry. And in that mistake, existence found its first foothold. It's tempting to imagine this as a deliberate choice, as though nature paused at the brink and refused to let itself vanish. But the truth is more unnerving. This survival was not inevitable. It was not even likely. It was a cosmic coin toss with only the smallest bias leaning toward matter over antimatter. One extra proton here, one unpaired electron there. Nothing that should have tipped the scales. But it did. And that slight, almost invisible tilt meant the difference between a universe filled with galaxies, planets, and the minds that question them, and a universe that blinked out the moment it began, a universe that never was. As the seconds expanded, the universe cooled just enough for this surviving matter to gather itself. The chaos softened, though only barely. Imagine the cosmos as an ocean of annihilation. every ripple threatening to erase the last scraps of existence. In those early moments, matter moved through the fire like hunted prey, dodging destruction by the narrowest margins. The cosmos was enormous in its energy, but fragile in its structure. There was no guarantee it would hold, no guarantee it would settle into something capable of endurance. And yet it did, step by trembling step. Each heartbeat of cosmic time brought new dangers, new possible endings, new ways the razor's edge might have snapped. Even the forces that governed this young universe were not fixed yet. They were still settling into their roles, still discovering the strengths that would either preserve existence or crumble it. Gravity at that time could have been stronger, a tiny fraction more, and everything could have collapsed back into a dense, silent knot, too weak, and matter would have drifted too far apart to form stars. The strong nuclear force could have fused particles too eagerly or not at all. Electromagnetism could have shredded the first fragile atoms before they had a chance to breathe. Each force tuned itself within a window so narrow it feels less like a window and more like the edge of a knife. The universe balanced itself on this blade, trembling but unbroken. Still, balance alone wasn't enough. Matter needed space, but not too much. It needed pressure, but not too little. It needed time, but only if that time unfolded in just the right way. Expansion had to slow, but not stop. Stretch, but not tear. Grow, but not explode into emptiness. A fraction faster and matter would have thinned into a cold mist, incapable of forming anything more complex than loneliness. A fraction slower and everything would have collapsed into a fireball with no room for breath. But the expansion rate settled into a perfect, almost too fast, almost too slow, a cosmic heartbeat in equilibrium. It is here, in this fragile corridor of possibility, that the universe first revealed its nature. A place where survival is not granted, but earned through impossible precision. A place where chaos strains toward order, not by overwhelming force, but by the softest nudge, the smallest imbalance, the tiniest refusal to disappear. And yet even this is not the full truth. Because if the early universe teaches us anything, it is that existence is founded not on certainty, but on near misses, on escapes so narrow they feel like accidents, on moments where everything could have gone wrong, and almost did. Consider what followed. Once matter survived its first trial, it still had to assemble itself into something recognizable. Quarks bonded into protons and neutrons into nuclei. But this bonding was not smooth. The forces involved had to operate with such delicate timing that a slight deviation would have made atoms impossible, too strong, and everything would have fused into heavy elements before the cosmos cooled enough to sustain them. Too weak, and nothing would have fused at all. Hydrogen would have been the only element, and a universe of only hydrogen is a universe without stars, without chemistry, without life. Another razor's edge, another impossible survival. As the first minutes stretched into hours and hours into years, the universe continued to test itself. Matter gathered into clouds. Those clouds threatened collapse. Radiative pressure threatened to tear them apart. For star formation to begin, the battle between gravity and heat had to reach a perfect deadlock, a tension that allowed collapse without catastrophe. Again, the universe walked a narrow path, and again it survived. Those surviving stars would become the forges of every element you and I are made of. But even they were born from tight margins. The earliest stars, massive and short-lived, burned with violence that bordered on self-destruction. Their nuclear reactions relied on balances so fine that if the strong force were altered by even a few percent, carbon, the backbone of life, would never have formed. If electromagnetism had been different by a fraction, oxygen would not bind the way it does. If gravity had differed by the slightest whisper, stars would have burned too fast or too cold to make the heavy elements at all. Every atom in your body is a monument to a sequence of narrow escapes, and yet we rarely consider how lucky this chain of survival really was. Not lucky in the human sense, no guiding hand, no destined outcome, but lucky in the statistical sense. The universe at every step had to pass through a doorway barely wider than a particle, a doorway that could easily have been closed, but it wasn't. For reasons we still don't understand, it stayed open long enough for matter to endure, for stars to form, for planets to take shape, for consciousness to arise and wonder how all of this began. This is the unsettling truth. We almost didn't happen, not metaphorically, not poetically, literally. The forces that shape reality could have erased the possibility of existence in less than a heartbeat. The early universe could have dissolved into light. The leftover matter could have vanished before the first second passed. The forces could have drifted into values that made structure impossible. But each time, the cosmos found a narrow path and followed it. And so we stand here now, billions of years later, built from the remnants of that improbable victory. Our existence is a fossil of that early imbalance, a quiet testimony to the particle that remained unmatched when everything else found its opposite. We are the result of a universe that survived by the slimmest margins and then kept surviving again and again, as though the razor's edge beneath it never dulled. As the act closes, a subtle tension lingers, because the universe has already escaped extinction once in its very first breath. And if it has done so before, we must ask the quiet, unsettling question it leaves behind. How many more narrow edges has it walked without us ever realizing? How did we get this lucky? In the moments after the universe's narrow escape from annihilation, reality stood trembling, hot, dense, unstable, overflowing with uneven patches of energy and directionless chaos. If left untouched, this chaos would have torn the cosmos apart before it ever found balance. The universe had survived its first trial, but it was far from safe. It was still a storm, asymmetrical and unruly. Any slight difference in density could have triggered premature collapse. Any pocket of excess energy could have ignited runaway expansion. It was a place that could not decide what to become. And then, in a moment so brief it is almost mythic, something extraordinary happened. The universe chose, not consciously, not deliberately, but through a process that remains one of the most mysterious in physics. The universe unleashed an expansion so sudden, so violent, so astonishingly fast that the normal rules of growth don't even apply. We call it cosmic inflation, though the word hardly captures what it truly was. In less than a trillionth of a second, the universe grew from smaller than a proton to larger than a galaxy. Space didn't stretch, it erupted. Distances didn't increase, they multiplied. A cosmos that should have been tiny and turbulent became vast, smooth, and surprisingly composed. Inflation was not chaos. Inflation was the opposite. It was the moment the universe found its stability. At the heart of this phenomenon was something entirely new, the inflaton field, a mysterious energy field that filled all of space-time, its behavior unlike anything we see today. When the inflaton field sat high on its potential energy curve, it behaved strangely. Instead of letting energy disperse, it caused space itself to expand exponentially. Like a ball perched precariously on a hill, the inflaton field lingered in an unstable position, holding immense energy, waiting for the slightest nudge. Once that nudge came, once the inflaton began its slow roll downward, space tore open in an instant. The universe didn't simply grow, it ballooned until every wrinkle, every jagged pocket, every patch of irregularity was swept flat. Imagine a sheet of paper crumpled into chaos, lines and folds twisting unpredictably. Inflation was the hand that smoothed the paper in one swift motion, eliminating the scars of its past. Before inflation, the universe was explosive, uneven, riddled with asymmetries. After inflation, it was uniform to 1 part in 100,000, a level of smoothness so astonishing that it seemed almost impossible. Temperatures across regions that should never have been able to communicate suddenly matched with near-perfect precision. Energy density became remarkably consistent, stretched across cosmic distances that light itself had not yet had time to cross. The horizon problem, the question of how such distant regions of space could be so similar, found its answer in this unimaginable growth spurt. Everything was once close enough to interact, and inflation took that closeness and magnified it into immensity. But inflation did something subtler as well, something more delicate. It didn't smooth the universe into flawless perfection. It left behind tiny imperfections, minuscule ripples in the fabric of space-time. These fluctuations were born from quantum uncertainty, the unpredictable jitter of particles and fields at the smallest scales. Inflation grabbed these microscopic tremors and stretched them across the cosmos. What should have been quantum wrinkles became the seeds of every galaxy, every cluster, every star. Without these slight deviations, the universe would have remained too smooth to form structure. A cosmic fog that never condensed, a sea without waves. These fluctuations became the great blueprint of cosmic architecture. Regions slightly denser than average attracted matter more strongly. Over billions of years, they grew into filaments and voids, into superclusters and spirals, into all the beauty we observe today. In a sense, inflation did not just prepare the universe for structure. It cast the first shadows of that structure, shadows large enough to shape the destinies of galaxies. It is here, in this quiet interplay between smoothness and imperfection, where the universe's delicate artistry reveals itself. Too much fluctuation, and the cosmos would have collapsed into black holes. Too little, and nothing would have formed at all. But inflation struck the balance, as though searching for the sweet spot between chaos and order. The flatness problem, another cosmic riddle, found resolution in the same moment. Before inflation, the curvature of space could have tilted in any direction, positive like a sphere, negative like a saddle, or flat like a sheet. These options should have diverged rapidly, creating wild geometries incapable of stable evolution. Yet today the universe appears astonishingly flat. Inflation solved this by stretching space so dramatically that any initial curvature faded into insignificance. Just as a balloon becomes locally flat when inflated enough, the cosmos became a vast, nearly Euclidean expanse. Inflation wasn't merely an expansion of size. It was an expansion of certainty, a resetting of cosmic conditions into a form that could persist. And yet, despite its enormous consequences, inflation did not last long. In one of the greatest paradoxes in cosmic history, the fastest change ever recorded ended almost instantly. As the inflaton field rolled down its potential and reached its lower energy state, inflation halted abruptly. All the immense energy stored in the field was released in a burst of reheating, a violent conversion of potential energy into particles, radiation, and momentum. The universe, once cold and empty during inflation, suddenly ignited. The firestorm of creation began anew, but this time on a foundation far more stable. Matter could form without fear of distortion. Forces could solidify into the constants we know. The stage was set, smooth and expansive, for the next chapters of cosmic evolution. But beneath that stability lingered a deeper philosophical question, one that physicists cannot easily answer. Why did inflation happen at all? Why did the universe possess an inflaton field? Why did it sit in an unstable state long enough to trigger exponential expansion? These questions drift beyond mathematics and into the domain of meaning. Inflation looks like a reset, a cosmic eraser that wiped the clutter of the early universe and replaced it with possibility. It appears as a moment where chaos was not allowed to dominate, where the universe refused to remain tangled in its own asymmetry. But nature does not choose in the way we understand choice, and yet something occurred, something that set the cosmos on a path toward coherence rather than dissolution. As inflation ended, the universe found itself with a new identity. No longer a chaotic firestorm, it was now vast, cool, predictable, and unexpectedly calm. The violent contraction and expansion of the earliest instants had been replaced by a quiet equilibrium. The echoes of inflation lived on only in the faint patterns of cosmic microwave background radiation, a ghost map of the universe's first brushstrokes. Those brushstrokes whisper to us even now, the universe is smoother than it should be, flatter than we expect, and structured enough to make life possible. Inflation did not just stabilize reality, it sculpted the conditions that would later birth stars, planets, oceans, consciousness, questions. Still, the mystery deepens. Inflation could have produced a universe too chaotic for structure or too uniform for galaxies. It could have failed to produce fluctuations altogether. It could have expanded endlessly without allowing matter to gather. But instead, it created a cosmos poised between emptiness and abundance, a cosmos where complexity could emerge. And in that emergence, a strange and quiet truth reveals itself. The universe's earliest moments were not merely energetic, but exquisitely tuned. This is the paradox that lingers behind inflation's mathematical precision. A force capable of unimaginable expansion somehow landed on the settings required for stability. A process rooted in randomness produced a universe where order could bloom. And in the end, inflation leaves us with a question that transcends science and drifts into philosophy. Why did the universe smooth itself? Why did it stretch its fabric into uniformity? Why did it allow imperfections only where they could blossom into galaxies? We arrive at a pause, a breath, a moment of awe, because inflation was more than the universe expanding. It was the universe aligning, preparing itself for everything that would follow. And in the silence that comes after understanding, a single haunting question rises. What force decided that chaos alone was not enough? They are just numbers, silent, indifferent, without shape or story. And yet, hidden within these values are the deepest secrets of existence: gravity's strength, the charge of the electron, the cosmological constant, the ratios that govern nuclear fusion. They sit quietly in the background of reality, never changing, never wavering, as if written into the universe before the universe even began. They do not ask to be noticed, but the moment you look closely, the moment you truly see them, a strange unease begins to rise, because these numbers should not exist the way they do, not with this precision, not with this balance, not with this almost impossible harmony that allows everything to unfold exactly as it has. Take gravity, the weakest of all forces by a staggering margin. Compared to the strong nuclear force, gravity is 1038 times weaker, a number so absurdly small that it feels like a misprint in the fabric of space-time. If gravity were even slightly stronger, stars would burn too quickly, collapsing under their own weight before life ever had the chance to appear. A universe filled with massive, short-lived firestorms and nothing more. If it were slightly weaker, matter would barely cling to itself. Stars would never ignite. Clouds of gas would drift endlessly, cold and lifeless, unable to gather into anything meaningful. And yet gravity rests in the perfect whisper-thin range between too strong and too weak, a cosmic tightrope walk where a tiny deviation collapses reality into chaos. Then there is the electron, that small carrier of charge whose mass defines the shape of chemistry itself. It determines how atoms bind, how molecules form, how stars burn, how DNA folds. If the electron's mass were altered by even a fraction, atoms would not behave the way they do. Electrons would orbit differently. Chemistry as we know it would collapse. Hydrogen, helium, carbon, oxygen, all dependent on this one number standing precisely where it stands. Again, the universe offers no explanation. The number simply is, and because it is, complexity can breathe. But the strangest number of all, the one that feels like an outright cosmic joke, is the cosmological constant, the value that determines the acceleration of the universe's expansion. It is small, unreasonably, incomprehensibly, laughably small. So small, in fact, that if you wrote it out, the zeros would stretch longer than most galaxies. A number so delicately fine-tuned that Nobel laureate Steven Weinberg once remarked, "It appears the universe knew we were coming." If it were slightly larger, the universe would have ripped apart too quickly for matter to form. If it were slightly smaller, gravity would have overwhelmed expansion, causing a collapse long before stars ever existed. The cosmological constant sits in a range so precise that the slightest deviation, an adjustment on the order of 1 in 10 or 120, would erase existence. It is not just fine-tuned. It is beyond fine-tuned. It is as if the universe is balancing infinity on the edge of a pin, and then we descend deeper into the nuclear forces, the engines of stars. The strong force is what binds protons and neutrons. The weak force governs radioactive decay and the alchemy of nuclear reactions. They too could have taken on almost any values, but they didn't. They settled into exact strengths that allow stars to burn steadily, not explosively. Too strong a strong force, and all hydrogen would have fused instantly in the early universe. No long-lived stars, no chemistry, no life. Too weak, and nuclei could never form. The universe would be left with a thin mist of particles, unable to build anything larger than loneliness. Even the ratio between the proton and electron masses, a seemingly arbitrary fraction, lies at the heart of everything we know. It determines the stability of atoms, the nature of molecular bonds, the structure of matter. If this ratio shifted slightly, chemistry would collapse into something alien or impossible. Stars would either burn too fast or fail entirely. Water, carbon, oxygen, the ingredients of life, would behave like strangers to one another. And so we stand before a pattern that feels less like chaos and more like design. Not intelligent design in the human sense, not a crafted universe in the theological sense, but a deeper design, a structure that seems to refuse randomness. These constants do not drift. They do not evolve. They do not respond to environment or time. They are set, fixed, permanent, as if locked into the universe before the first photon escaped into darkness. When we call the universe fine-tuned, we are not speaking poetically. We are speaking literally. These numbers form a code. Alter any one of them even slightly, and the entire system collapses. But the deeper we look, the stranger it becomes. Because these constants are not only precise, they are independent. There is no known reason gravity should have the strength it does. No known reason the cosmological constant should be near zero, but not exactly zero. No reason the electron should have the mass it does. Physics offers equations, but the equations rely on the constants, not the other way around. We can describe the universe with breathtaking accuracy, but not explain why its foundation rests on these numbers instead of others. This is the existential tension at the heart of science. For centuries, we believed that deeper understanding would reveal deeper necessity, that the universe had to be the way it is. But the constants suggest the opposite. The universe did not have to be this way. It could have been cold, chaotic, sterile, violent, or short-lived. Instead, it emerged from the void with a recipe that allows stars to shine gently for billions of years, planets to orbit stably, molecules to assemble, and consciousness to awaken and ask questions. And this leads to suspicion, the quiet kind that creeps into the mind when the coincidence becomes too much to ignore. Why do the numbers land exactly where life can emerge? Why does the universe seem so generous with its stability? Why does reality behave as if calibrated for complexity? Some physicists argue that perhaps countless universes exist, each with different constants, most sterile, a few capable of harboring structure. If that is true, then we simply inhabit one of the rare universes where the numbers happen to line up. But even this explanation carries its own discomfort, because it implies that our universe is improbably lucky among unimaginable possibilities. Others argue that perhaps deeper laws exist, laws we have not yet uncovered, that link these constants together in a way we cannot see. But until those laws emerge, if they ever do, the fine-tuning remains a mystery, a whisper of order in a place that should be chaotic. As we tour these cosmic values, gravity's weakness, the electron's mass, the nuclear force's precision, the cosmological constant's unimaginable smallness, a single realization grows sharper. Almost none of these numbers make sense by themselves. They feel like settings placed at the edge of possibility, as if the universe were poised between existence and oblivion, and chose against overwhelming odds the narrow corridor where life is allowed to bloom. In the end, we are left with a fragile awe. These constants are not just numbers. They are the silent architects of reality. They govern the birth of stars, the glow of galaxies, the chemistry of oceans, the beating of hearts. They form the underlying rhythm to which everything moves. If even one of them were different, not wildly different, just slightly, the universe would be dark, structureless, lifeless, a cosmic shadow without story. And so our journey through the settings of the universe ends with a truth that feels almost impossible. Change any of these numbers, and the universe goes dark. In the earliest moments of existence, before particles had identities, and before forces knew their own strengths, the universe was guided by something deeper than matter or energy. It was guided by symmetry, a kind of hidden blueprint woven into the fabric of reality. Not symmetry in the simple geometric sense, but a profound mathematical balance in which distinctions did not yet exist. Up and down were the same, left and right were indistinguishable. Particles had no mass, no charge, no character. The forces we know today were fused into a single elegant unity. The universe had not yet chosen who anything would become. It simply existed as pure potential, balanced on the edge of perfect sameness. To us, symmetry feels like stillness, like a pattern repeating without flaw. But in physics, symmetry is power. It is the rule that says, if you change this, nothing changes. It is invariance, the idea that the laws of nature hold regardless of where you stand or how you move. In that primordial state, the universe obeyed a symmetry so sweeping that the distinctions underlying our reality had not yet formed. Electromagnetism and the weak nuclear force were one. Time and space behaved with uniform rhythm. Matter had not yet learned to resist motion. Even the inflating field, as it drove the early expansion, moved through a landscape defined by symmetry's quiet constraints. But perfection cannot build, it cannot evolve, it cannot create stars or galaxies or life. Perfect symmetry is empty of features, a blank page waiting for the first ink to spill. And so inevitably, symmetry broke. This breaking was not destructive, it was creative. When a perfect pattern fractures, it reveals what was hidden inside it all along. Think of a frozen lake beginning to crack, revealing depth beneath the smooth surface, or a mirror shattering into pieces that catch the light in new ways. In that same spirit, the universe allowed its original symmetry to collapse into asymmetry. And from that collapse came the first hints of structure. The electroweak symmetry broke when the Higgs field settled into a non-zero value. Before this moment, particles were massless, moving at the speed of light, indistinguishable from pure radiation. But when the Higgs field permeated space, it changed everything. It introduced resistance, allowing some particles to slow down to gain the property we call mass. W bosons and Z bosons, carriers of the weak force, became heavy. Photons remained massless, free to roam as light. A single symmetry breaking divided one force into two and reshaped the destinies of particles forever. It is tempting to imagine this as a dramatic explosion, but in truth, it was quiet, a smooth, spontaneous shifting of the universe's ground state. Like a ball rolling down from the top of a hill into a valley, the Higgs field moved into a new configuration, and reality followed it. What had been unified became distinct. What had been identical became varied, and that variety was the spark of all complexity. Another symmetry fractured when the strong nuclear force separated from the electroweak force. This earlier breaking determined how quarks would bind, how protons and neutrons would emerge, how atomic nuclei would form billions of years later inside the hearts of stars. Again, the symmetry did not merely shatter, It rearranged itself into a new pattern with new rules, each one enabling the next step toward a universe filled with structure. As time flowed forward, every level of reality repeated this dance. Symmetry offered simplicity. Its breaking offered possibility. Particles with identical properties split into families. Forces that once mirrored each other diverged into distinct interactions. Even the distribution of matter across the cosmos, the cosmic web of filaments and voids, traces its origin to tiny imperfections stretched across space during inflation. Each imperfection was the result of a symmetry not quite holding, and each one became the seed of something vast. To appreciate this fully, imagine the universe without symmetry breaking. No particle would have mass. No atoms would exist. Forces would not have the subtle balance that allows stars to burn steadily instead of collapsing or evaporating. Everything would be uniform, silent, motionless in its sameness. A universe without symmetry breaking is not a universe at all, not in any meaningful sense. It is only a canvas without paint. It is the fractures that gave it color. In this sense, symmetry breaking is the closest thing cosmology has to a creative act. The universe did not build itself by assembling pieces one by one. It emerged from the falling away of possibilities, from the narrowing of what could be into what is. When electroweak symmetry broke, reality gained texture. When the Higgs field chose its value, it gave particles identity. When the early energy fields collapsed into new configurations, they carved the paths along which galaxies would eventually gather. Even matter survival itself, that slight excess of matter over antimatter, is believed to be tied to a broken symmetry, CP violation. A tiny imbalance in how nature treats matter versus antimatter tilted the scales, allowing the 1 in a billion particles that survived annihilation to form the atoms of your body. Without that broken symmetry, the universe would be filled only with light, with no structure, no galaxies, no minds to wonder how it began. And so we begin to see that symmetry is not destiny. Symmetry is the starting point from which destiny emerges. It is the silent blueprint beneath the visible chaos. Every time the universe fractured its own balance, it was not destroying order. It was trading one kind of order for another, deeper, richer, more capable of supporting complexity. Mathematically, these symmetries are encoded in group structures, elegant frameworks of transformation that preserve certain quantities. Physically, they manifest as conservation laws, energy, momentum, charge. Philosophically, they represent the universe's preference for harmony. But harmony alone cannot produce diversity. A melody must break from its opening chord to become music, and the universe in all its vastness followed that same rule. The beauty lies in how the breaking happens. It is never random. It is never catastrophic. It is always balanced between too soon and too late, too strong and too weak. When symmetry breaks too violently, the universe collapses into disorder. When it fails to break at all, the universe remains sterile. But our universe found the exact sequence of cracks, the precise moments where the fracture would lead not to ruin, but to architecture. Symmetry breaking determined which particles could exist, how they would interact, and what they would become over time. It shaped the story of forces, from the strong nuclear force that binds atomic nuclei to the electromagnetic force that illuminates our nights. It influenced the cosmic microwave background, the first galaxies, the stars that fused heavy elements, the planets that cooled, the oceans that formed, the chemistry that learned to self-organize, the spark of consciousness that emerged billions of years later to gaze backward at the pattern that made it possible, a harmonious beginning fractured into complexity, a perfect blueprint cracked open into creation, and yet it never lost its underlying elegance. Even today, the mathematics of the Standard Model, our best description of particles and forces, is built upon symmetries, gauge invariances, rotational symmetries, local transformations. Beneath the noise of everyday experience lies a structure almost too beautiful to believe. Reality is a broken symmetry wearing the mask of complexity. This realization evokes a strange kind of awe. The universe is not just fine-tuned. It is composed like art. It did not emerge fully formed. It unfolded layer by layer as balance gave way to variation. The perfection of its early symmetry was not its destiny, but its prelude. The crack was the beginning of the story. And so we are left with a thought that lingers softly in the mind. Perhaps the elegance we observe, the precision of constants, the stability of forces, the coherence of cosmic structure arises not because the universe is perfectly symmetric, but because its imperfections are perfectly placed. Perhaps the universe is balanced because the cracks in its symmetry fall exactly where they must. Perhaps the universe is balanced because its imperfections are perfectly placed. Life began long before life existed, long before oceans curled around continents or cells learned to divide. The universe was preparing the conditions that would one day allow something delicate, fleeting, and self-aware to appear. But those conditions were not inevitable. They were the result of a long cascading chain of balances, so precise that each one feels like a quiet miracle. Not a miracle in the supernatural sense, but in the statistical sense, an outcome so unlikely that it forces us to pause, to breathe, to wonder how all of this managed to align so gently. In the beginning, the universe was cold space and silent radiation. The earliest stars had only hydrogen and helium to work with, the raw, simple elements forged in the minutes after the Big Bang. There was no carbon yet, no oxygen, no iron, none of the metals that life depends on. For life to become possible, the universe first needed stars massive enough to crush hydrogen into heavier elements, but not so massive that they collapse before spreading those elements outward. These first giants were short-lived, but their death throes seeded the cosmos with everything from carbon to calcium. They were the universe's first alchemists. But their work was only possible because of another delicate balance, the triple alpha process. In the hearts of stars, 3 helium nuclei must collide within a fraction of a second to form carbon. If the strong nuclear force were slightly different, these collisions would fail. Carbon would be rare or non-existent. No DNA, no plants, no animals, no minds, and yet the laws of physics allowed just enough stability in that reaction to fill the universe with the chemistry of life. A star, a sphere of plasma 1,000,000 times the size of Earth, became the first great craftsman of complexity. And it succeeded only because the constants of nature rested in tiny windows where the improbable becomes possible. Once heavy elements existed, they drifted into clouds that collapsed into new generations of stars. These stars were cooler, more stable, longer lived. They created galaxies with spiraling arms and gentle rotations. But even galaxies required balance. Too much density, and everything would collapse back into black holes. Too little density, and stars would drift apart before planets could form. The cosmic average mass density, a number that looks meaningless on paper, determined whether the universe would be a chaotic storm or an infinite emptiness. Instead, it became something between the two, structured but not suffocating, spread out but not barren. It was within these galaxies that planets began to assemble. Dust grains collided, stuck, and grew. But planetary formation is not guaranteed. It depends on metallicity, the fraction of heavy elements available in a star-forming region. If the universe lacked enough metals, planets like Earth could never form. If it had too many, early stars would have burned too violently for stable systems to take shape. Instead, metallicity rose gently over billions of years, increasing just enough to allow worlds with solid crusts, liquid oceans, and complex chemistry to emerge. And still, the universe was not done fine-tuning. Planetary systems require stable orbits, a balance between gravitational pull and orbital velocity. Too close to the star and the planet becomes an inferno. Too far and it freezes into silence. We call this the Goldilocks zone, not too hot, not too cold, but even this is an oversimplification. Life needs more than warmth. It needs chemical gradients, plate tectonics, magnetic shielding, long-term climate stability, and oceans that remain liquid for billions of years. It needs moons to stabilize tilt. It needs the right amount of atmospheric pressure to allow water to cycle instead of boiling away or collapsing as ice. It needs a star that burns steadily, not one that flares unpredictably. And every one of these requirements depends on conditions set long before planets existed. The strength of gravity determines atmospheric retention. The mass of the proton determines chemical behavior. The cosmological constant shapes the growth of galaxies. The nuclear forces dictate the lifetime of stars. Life is not just a biological phenomenon. It is a cosmic consequence. The end of a long, fragile chain reaction initiated moments after the universe began. Consider water, the solvent of life. Its properties, its expansion when frozen, its high heat capacity, its ability to dissolve so many compounds, depend on the angle of hydrogen bonds, a small detail of electromagnetism that could have been otherwise. If water froze by contracting, oceans would sink their ice, freezing from the bottom up and never melting completely. A frozen world cannot produce chemistry, but because water expands when it freezes, ice floats and planets maintain cycles of thaw and renewal. The physics of hydrogen bonding became the quiet guardian of habitability. Or consider carbon, the backbone of organic molecules. Carbon can form stable bonds with itself, creating chains, rings, frameworks, all because of the quantum structure of its electron shells. Silicon, though similar, lacks this graceful versatility. Life chose carbon not because it was preordained, but because the universe provided a narrow window where carbon chemistry was robust, abundant, and flexible enough to create organisms that could eventually ask questions. Even time became a requirement. Life did not appear instantly. It needed billions of years of stellar evolution, planetary cooling, and chemical experimentation. A universe that expanded faster would not have had time to form galaxies. A universe that expanded slower would have collapsed before complexity emerged. The timeline of existence, from the first star to the first breath, is written into the cosmological parameters set at the beginning. When we step back, the pattern becomes clear. Life arose not from a single miracle, but from a sequence of conditions, each one relying on the previous, all connected across unimaginable scales. From quantum fluctuations stretched during inflation, to nuclear reactions in stars, to planetary orbits, to the fragile balance of a planet's climate, to the folding of proteins inside cells, everything aligns. It is a universe that does not simply allow existence, it allows becoming. And this is perhaps the most profound revelation. Life is not a random intruder in a hostile cosmos. It is the result of a universe that has spent billions of years arranging itself into a stage where complexity can flourish. It is the emergent property of a cosmos tuned not for comfort, but for possibility. Life feels improbable, yes, but given the right conditions, it also feels inevitable. A symphony played on cosmic scales, where each note depends on the harmony of all the others. Yet the fragility remains. Change the density of the early universe and galaxies fall apart. Change the temperature of stellar cores and carbon never forms. Change orbital mechanics and planets drift into darkness or flame. Change chemistry and molecules fail to bind. Change atmospheric conditions and oceans never stabilize. Change the timeline and evolution never finds its foothold. It is in that fragility that awe transforms into something deeper, gratitude. Because the universe did not need to be this warm, this stable, this generous with time and structure. It could have been colder, hotter, denser, thinner. It could have been a place where matter collapsed too quickly or never gathered at all. Instead, it became a cradle, harsh, vast, indifferent, and yet somehow perfectly balanced to let life emerge and gaze upward. And so this act closes with a whisper of delicate wonder, a reminder of the knife edge on which everything rests. If the universe were colder, hotter, denser, thinner, we would not be here to ask why. The deeper we journey into the architecture of reality, the more the universe begins to look like a puzzle that has already solved itself. Every constant, every symmetry, every spark of structure seems arranged with eerie precision, as though the cosmos were tuned for the eventual rise of consciousness. But this idea, seductive, dangerous, and strangely comforting, comes with a paradox at its core. It is the anthropic principle, the notion that we should not be surprised the universe permits life, because if it didn't, there would be no one here to be surprised at all. At first glance, this feels obvious to the point of triviality. Of course, we exist in a universe compatible with life. Where else could we be? But the moment you sit with this thought, the ground shifts beneath you, because this principle suggests something unsettling. Our observations are not neutral. They are biased by the simple fact of our existence. The universe appears fine-tuned, not necessarily because it was constructed that way, but because only a fine-tuned universe can host observers who wonder about tuning. It is a loop, self-referential, slippery, impossible to escape. The more you think about it, the more the distinction between the observer and the observed begins to blur. This is the weak anthropic principle, the idea that our existence filters what we can observe. In a multiverse with countless domains, we would naturally find ourselves in the one where the constants allow life. There is nothing special about this domain, except that it contains beings capable of asking these questions. The others, universes with too much gravity, too little electromagnetism, too chaotic an expansion, remain silent because silence is all they can produce. No stars, no chemistry, no witnesses. But then there is the strong anthropic principle, a far stranger proposition. It suggests that the universe must be such as to give rise to observers, that the conditions for consciousness are somehow built into the fabric of reality. This is not saying the universe was designed for us. Rather, it hints that universe is capable of forming selves, observers, minds, question askers, possess a kind of internal necessity, a pressure toward complexity, a tendency toward the emergence of beings who can reflect on their own origins. This idea borders on the metaphysical, yet it lingers because the alternatives are equally dizzying. If the universe is not compelled to produce observers, then the probability of such an emergence appears vanishingly small. And yet here we are, complex, conscious, aware, and capable of mapping the cosmic microwave background to its first trembling moments. The fact that the universe not only allows life, but allows life that can understand its own fragility feels like more than coincidence. Or perhaps it only feels that way because we are inside the story, not outside it. This is the heart of the anthropic paradox. Every explanation folds back into itself. We search for meaning in fine-tuning, only to discover that our search is shaped by the very conditions we're trying to explain. We look at the universe and see perfection, but only because imperfection would have erased the possibility of seeing anything at all. Consciousness becomes both the detective and the suspect, the mirror and the reflection. In this looping logic, a strange kind of dizziness takes hold. Did the universe create the conditions for life, or did life create the illusion of conditions being just right? Are we uncovering cosmic truth or merely glimpsing the boundary of what can be observed from within a narrow slice of possibility? The question spirals downward, deeper and deeper, until the line separating physics from philosophy dissolves. Consider this: the laws of physics appear constant and universal, but we only know this because we are capable of perceiving order. If consciousness could not arise in universes with unstable laws, then those universes would remain forever unobserved. Their chaos would be invisible not because it isn't real, but because no eyes exist to witness it. In this view, the universe seems perfect because only perfection, or something close to it, can produce minds that experience the sensation of perfection. The observer becomes inseparable from the structure of reality itself, not because consciousness shapes the universe, but because the universe shapes what consciousness can ever know. It is an epistemological horizon, a boundary beyond which meaning cannot cross. Like trying to see your own eyes without a mirror, the universe's self-awareness is always indirect. We are that mirror. As we stare into this reflection, we begin to realize that the anthropic principle is not merely a scientific idea. It is a philosophical riddle, a kind of cosmic koan that asks us to contemplate our own improbability. It provokes questions that cannot be resolved with equations alone. Why should there be laws at all? Why should they be stable? Why should complexity be permitted to form in the first place? The anthropic principle does not answer these questions. It reframes them. It tells us that perhaps these questions can only be asked in universes where asking is possible. And that reframe comes with an unsettling twist. If we exist because the universe permits us, then the universe's apparent fine-tuning is not evidence of intention. It is evidence of selection. We are here because we could not be anywhere else. Life emerges where it can. consciousness blooms where conditions allow, and observers arise only in universes compatible with observation. This does not diminish the wonder of existence, it heightens it, because it means the universe did not need to be generous. It did not need to be expansive or stable or rich in chemistry, but in one tiny branch of possibility, it was. Still, the strong version of the anthropic principle refuses to fade. It whispers that perhaps consciousness is not an accident. Perhaps the emergence of observers is woven into the deep story of reality, not as purpose, but as consequence. In such a universe, complexity is not merely allowed, but inevitable. Order arises from chaos, mind arises from matter, and reflection arises from mind. In this interpretation, the universe becomes a place that leans toward self-awareness, though not in any intentional or teleological sense, simply because the laws that govern it allow structures to build upon themselves. This idea evokes a peculiar form of awe, not the awe of grandeur or beauty, but the awe of self-recognition. The realization that we are not separate from the universe, but expressions of its deepest tendencies. That when we look outward, we are also looking inward, because the same laws that govern galaxies also govern the neurons firing in our brains. The observer and the observed are not entirely distinct. They are linked through the logic of emergence. And so we spiral further. Did the universe fine-tune itself? Are we the byproduct of countless cosmic lotteries? Or is our very ability to ask the question the reason the universe appears tuned in the first place? The anthropic paradox offers no clear answer, only the invitation to stand at the boundary of what can be known. Perhaps that is the point. The paradox is not meant to explain the universe. It is meant to reveal the limits of explanation. It is a reminder that meaning is shaped by perspective, and our perspective is bound to the narrow conditions that allow us to exist at all. The universe feels perfect because we are the descendants of the universes that permitted perfection to matter. And so this act ends in existential silence, in the soft hum of a question that has no conclusion. Maybe the universe seems perfect because imperfect universes leave no witnesses. In the search for meaning, fine-tuning feels like a whisper from the universe, a whisper suggesting purpose, precision, some hidden logic guiding the unfolding of everything. But not everyone agrees that the universe requires such intention. Some physicists look at the same exquisite balance and see something far stranger, the possibility that our universe is not alone, that the cosmos we inhabit is merely one bubble in a vast and infinite ocean of universes, each with its own laws, its own constants, its own beginning and end. In such an ocean, fine-tuning would no longer be a miracle. It would simply be the outcome of cosmic probability. A lottery with infinite attempts cannot fail to produce a winning ticket. The idea is unsettling. It dilutes meaning even as it expands possibility. But to understand why the multiverse emerged as a serious contender in modern physics, we must return to the moment inflation ended, that explosive stretching of space-time that shaped the structure of everything. Inflation did not necessarily stop everywhere at once. In some models, it ended only in isolated regions, forming pocket universes, while inflation continued endlessly elsewhere. This is eternal inflation, one of the most provocative ideas in cosmology. It suggests that our universe was just one patch where inflation cooled enough to produce matter and energy, while other patches continued expanding, budding off their own universes in a never-ending cascade. In this view, creation is not a singular event but an ongoing process. Universes blooming from the inflating fabric like seeds scattered across infinity. Each universe may have different constants, different symmetries, different values for gravity or the cosmological constant. Some burst into chaos and collapse in seconds. Others expand too fast for matter to form. Most remain sterile. A few, perhaps a very small few, are stable enough to form galaxies, stars, chemistry, life, but only one will ever feel familiar to us, the one we inhabit, the one whose conditions allow observers to look around and marvel at how unlikely everything seems. Eternal inflation reframes existence. It suggests that the universe did not need perfection. It only needed a lottery large enough to guarantee rare outcomes. But eternal inflation is only one doorway into the multiverse. Quantum mechanics offers another. In the quantum multiverse, often associated with the many worlds interpretation, every quantum event spawns branches of reality. Every time a particle can go left or right, every time an atom can decay now or later, every time a neuron in your brain can fire or stay silent, the universe splits. Most of these branches diverge in ways too subtle to ever notice. Others diverge dramatically. In this framework, reality is not a single timeline, but a vast fractal tree of possibilities. We experience one branch, but all branches exist. Applied to cosmology, this interpretation becomes dizzying. It implies that every possible configuration of matter, every possible universe with every possible constant, may have its own branch somewhere in the quantum tapestry. Fine-tuning becomes merely the observation that we live in one of the branches where consciousness could arise. The other branches, countless and silent, remain forever unobserved. Yet another doorway lies in string theory, not through quantum branches, but through geometry. String theory suggests that the fundamental ingredients of reality are tiny vibrating strings, whose vibration patterns determine particle types and forces. But the theory does not produce a single universe. It produces a landscape, a massive collection of possible vacuum states, perhaps 10,500 or more. Each vacuum corresponds to a different universe with its own physical laws. Gravity could be stronger in one universe, weaker in another. Electromagnetism could be absent. Time could behave differently. Space might twist in ways unimaginable. If the string landscape is real, then our universe is simply one coordinate in a vast cosmic catalog, a catalog so large that even extremely rare configurations, like the one that permits life, would still appear countless times. In this perspective, fine-tuning is just geography. We live where living is allowed, but the multiverse becomes stranger still. Brain cosmology suggests that our universe may be a three-dimensional membrane floating in a higher dimensional space. Other brains could exist parallel to ours, each containing its own universe with its own laws. Sometimes these brains might collide, creating events that resemble big bangs. Sometimes they might drift silently, unaware of one another. If such collisions are common, the universe may be cyclic, expanding, contracting, reborn endlessly. Each cycle could bring new constants, new boundary conditions, new chances for life to emerge. In a cyclic universe, fine-tuning becomes a moving target, not a single perfect arrangement, but a pattern arising through repetition across cosmic epochs. The universe might not be finely tuned because it was designed that way, but because only cycles with the right parameters survive long enough to produce complexity, a kind of cosmic natural selection. All these theories, eternal inflation, quantum branching, string landscapes, brain worlds, cyclic cosmoses, differ vastly in method and implication. Yet they share a haunting common thread: the idea that our universe is not the only one, that what we call everything may be just one shard of a much larger whole. Emotionally, this idea cuts both ways. On one hand, it can feel liberating. If there are infinite universes, then every possibility blooms somewhere. Reality becomes a garden without boundary, rich beyond imagination. On the other hand, it evokes dread. If infinite universes exist, then ours is not special. Our meaning becomes diluted across infinity. Our existence becomes one outcome among countless others. The delicate fine-tuning that seemed to whisper intention now becomes the statistical inevitability of an infinite sample size. And yet, something deeper stirs beneath this unease. Because the multiverse does not diminish wonder, it multiplies it. It suggests that reality is not constrained by a single set of rules, but is instead an exploration of every rule that can be written. It transforms the story of creation from a singular event into a cosmic symphony where every variation is played. Still, questions linger. If there are infinite universes, how do we define special? If fine-tuning can be explained by selection across infinity, does that mean our universe lacks meaning? Or does it mean meaning is simply broader than we imagined? Perhaps the discomfort we feel is not evidence against the multiverse, but evidence of our own limitations, our instinct to seek singular answers in a cosmos that may refuse singularity. There is also the unsettling possibility that we can never confirm the multiverse empirically. Universes may be sealed off from one another, unreachable, unknowable. We can infer, hypothesize, construct models, but never observe them directly. If this is true, then the multiverse becomes a philosophical escape hatch, a way for the universe to avoid answering difficult questions by giving us a framework where questions dissolve into infinity. And yet, even if the multiverse cannot be tested, it remains compelling. Because the alternative, that our universe alone carries the exact and improbable recipe for life, is equally mysterious. Either the universe is unique beyond comprehension, or it is one of countless attempts. Both possibilities stretch the mind, both challenge our assumptions, both force us to confront the vastness of what may exist beyond the horizon of observation. And in the end, perhaps these possibilities do not compete. Perhaps the multiverse is not meant to explain away fine-tuning, nor is fine-tuning meant to dismiss the multiverse. Perhaps they are two ways of expressing the same idea: that reality is larger, deeper, and more enigmatic than anything our species has yet imagined. As our thoughts drift toward the infinite, a final question takes shape, soft, provocative, and impossible to ignore. If there are infinite universes, is ours still special, or just the one that noticed? In the end, we return to the paradox we began with, the strange harmony of a universe that should not exist in such a delicate form, yet does. Not perfectly, not intentionally, but meaningfully enough for life to gain a foothold and begin asking questions. Every constant, every symmetry, every fracture and fluctuation formed a chain of conditions that led improbably to awareness. But the closer we look, the more it becomes clear that this balance is not a message written for us. It is the stage upon which we happen to emerge, shaped by its contours, sculpted by its constraints. Life did not arrive because the universe was fine-tuned for it. Life arrived because it adapted itself to the only universe where adaptation was possible. And so the fine-tuning dissolves. What once felt like intention softens into consequence. What once resembled design transforms into survival. We are not the reason the universe is balanced. The universe's balance is the reason we exist at all. The harmony we perceive is partly real, partly reflection, a mirror held up to our longing for order. In a cosmos that remains at its core indifferent yet astonishingly fertile, there is peace in this realization, not the peace of certainty, but the peace of humility, the understanding that we do not need to solve the universe to feel wonder within it. The cosmos does not owe us meaning, and yet it gives us the chance to create meaning simply by being here to witness it. In that quiet, the final truth settles. The universe is perfectly balanced, because it is the only one we can survive long enough to marvel at.